This is section 5.2, the addition rule and complements. Two events are considered disjoint if they cannot both occur at the same time. They cannot both occur at the same time. So they're considered disjoint if they cannot both occur at the same time. So if I flip a coin, I cannot get heads and tails at the same time. I either get heads or tails. Those are disjoint events. When I roll a die, I can either get a 1 or a 2. I don't get both at the same time. Disjoint events are also called mutually exclusive. So exclusive means excluding, and so mutually exclusive means they exclude each other. So in order to help us kind of see these events, we use what are called Venn diagrams, and you might have seen those before from grade school. The different circles, sometimes they do not overlap, sometimes if you push them together they do overlap. We'll look at kind of both instances here. We're going to start with disjoint events where they do not overlap. So let's think about the numbers 0 through 9 as if they were on chips, like little poker chips. So we've got the numbers 0 through 9. If it helps, you can kind of draw yourself little chips. So think of this kind of like a carnival game. One chip has a 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And let's say they all have an equal chance of being drawn out of a bag. And so let's think about two different events. The first event, F, choose a number greater than or equal to 8, which are just the chips 8 and 9. So event F has the chips 8 and 9, two different outcomes. And then event E, choose a number less than or equal to 2, which would be 0, 1, or 2. So event E has the chips 0, 1, and 2. These are considered disjoint events because they cannot both occur at the same time. They don't share any chips. And you also have the sample space S, which is this box around it, which are all the other chips that are not in these two events. So chip 3, 4, 5, 6, and 7 are all in the sample space, but not in either of these two events. So this is where the addition rule comes in for disjoint events. So this is only for the two events do not overlap. If we wanted to calculate the probability that event E or event F occurs, you would calculate the probability of event E and add it to the probability of event F. So this is the addition rule for, again, disjoint events. If E and F are disjoint or mutually exclusive, then the probability of one or the other means you just add them together. So let's see, the probability of E or F for our example. Event E has 3 out of 10, plus event F has 2 out of 10, for a total of 5 out of 10. And we can write that as 0.5 or 50%. So the probability of event E or F occurring is 50%. You can see there's 5 chips in the events. There's 5 chips not in the events. So on that same note, still thinking about chips, let's think about another example, adding a new event that we're going to call G, and G is choose a 5 or 6. So we still have event E, 0, 1, and 2. We still have event F, 8 and 9. Now we have this new event G that's still disjoint or mutually exclusive, 5 or 6. And there's still a few chips that are not included. 3, 4, and 7 are still not part of any of these events. So to get the probability of event E or F or G, we're just going to add up each one. We said the probability of event E is 3 out of 10. Probability of event F is 2 out of 10. And then this new probability of event G is also 2 out of 10. If we add all those together, that gives us 7 out of 10, or 0.7. And you should see 7 chips are in the events, 3 chips are not. So 7 out of 10, or 0.7. There's some more examples in your textbook if you want to just see this again. This is very simple for disjoint events. You just add up the different probabilities. This formula is also here in your formula sheet. Probability of E or F for disjoint events is E plus F. Don't forget about this. You can use this on every test. And then same thing for however many you have disjoint events, you just add them all up, however many you have. Now let's talk about what's called the general addition rule. This one is a little different. The general addition rule works for disjoint and overlapping events. So disjoint has its own separate rule, but this rule works for everybody. So this is if an overlap occurs, meaning one outcome is in both categories, and we'll look at an example of that in just a second, then we must not count the overlap twice. So it cannot be included with both calculations. So still using the digits 0 through 9, if we have event E, choose an odd number. So event E, the odd numbers would be 1, 3, 5, 7, and 9. And the event F, choose a number less than or equal to 4. That would be 0, 1, 2, 3, or 4. So these two events are not disjoint. They're not mutually exclusive. There are some digits that fit both categories. So the number 1 appears in both, and the number 3 appears in both. It's both odd and less than or equal to 4. So when we make this Venn diagram, we have event E, and in this little crescent moon section, we're only going to put the events or the chips that don't overlap. In the middle, we're going to put the ones that overlap. And on the other side, we'll put the events in F that do not overlap. So you don't repeat anything here. You put just E, both E and F, and then just F. So you'll notice each number only appears once here, whereas listing the events here, you see these two numbers repeat. So the general addition rule to calculate the probability of E or F in this situation is you get the probability of event E. There are 1, 2, 3, 4, 5 digits in event E out of 10. The probability of event F, there are 1, 2, 3, 4, 5 digits in event F. And I forgot to include the numbers that are not in either. That would be the numbers 6 and 8 are not in either of these events. So there's 5 in event E, there's 5 in event F, and what we need to do, the difference between this one and the disjoint rule, is to subtract the overlap, the probability of E and F, which is 2 out of 10. So the general addition rule for E or F is E plus F minus the probability of E and F. So this is to get E or F. We're going to do 5 out of 10 plus 5 out of 10, just like we did for disjoint, but we're going to subtract the 2 that were counted twice. So the 1 and the 3 are part of this 5 and that 5. So adding these together, we've counted these two outcomes twice, so we subtract that overlap. And that should give us 8 out of 10. Now that 8 out of 10 matches with what we see here. There's 8 options out of 10 total. You'll see the 2 excluded, 8 included. So your final answer should match your Venn diagram. You won't always have a Venn diagram, which is why we have this formula, but Venn diagrams, if it's simple enough, Venn diagrams can really help. So that's called a general addition rule. There are 4 pieces of information here. There's the probability of E or F, the probability of E, probability of F, and the probability of E and F. So with these 4 pieces of information in your homework, they're going to give you 3 of them and ask you to find the 4th. So they might give you these 3 and ask for this one. They might give you these 3 and ask for that one, and anything in between. So just be ready to fill in what you have and solve for what you're missing. It's just very simple algebra. This formula is also in your formula booklet. It's called the general addition rule. So there it is. It looks just like the disjoint rule, except it subtracts the overlap. So this works for any 2 events, even if they are disjoint. Because if they're disjoint, then there is no overlap, and you're left with the same formula. So that's why they call it the general addition rule. Alright, so let's look at an example with a deck of cards. And this is a standard American deck of cards. I know some of my international students might not know what an American deck of cards is, and that's okay. There's a nice graphic on page 246 of your textbook. If you're not familiar with an American deck of cards, I strongly recommend looking at that graphic. Or you can go to the dollar store and get yourself a deck of cards. So they're just a standard deck of cards. There's a total of 52 cards. And so if you're not familiar with that, you might want to jot that down. There's a total of 52 cards. There's 4 what they call suits or patterns on the card. Jokers don't count. So let me show you those 4 patterns. So there's 4 what they call suits. The suits are hearts, which look like a heart. And then you've got diamonds, sharp pointed diamonds. And then you've got clubs, which I always called clovers growing up. So that's clubs, like a little clover. And you have spades. Spade kind of looks like a shovel, like to garden with, a gardening spade. The clubs and the spades are black, so half the cards are black and half the cards are red. So 50% black, 50% red, half and half. And then there's 13 cards in each suit. And again, you might be very familiar with this. I love playing cards, so if you play cards all the time, this is no big deal. If you've never seen a deck of cards like this before, you might want to take a minute and kind of study how this all works. There's 13 cards in each suit. Let's see if I can quickly find them all. There's the numbers 2 through 10. There's aces. I don't know if I'm able to quickly find these, but I'm going to try. There's kings, queens, jacks. Okay. So there's an ace. There's 4 different aces, one of each suit. Then there's the numbers 2 through 10. So 2, 3, 4, 5, 6, all the way up to 10. I'm not going to find all those. 2 through 10. So 2, 3, 4, 5, 6, 7, 8, 9, 10. And then there's a jack, which is the J of each suit. There's a queen of each suit. And there's a king of each suit. So there's 13 cards, ace through king, of each suit. So again, if you're familiar with the deck of cards, no big deal. If not, there's a nice graphic of all the cards on page 246. Or you just go to the dollar store and get yourself a deck of cards just to become more familiar with how they work. If you get a deck of cards, the jokers don't count. So that's not part of the deck. You won't see these jokers on that graphic because they're not considered part of the deck of 52. Alright, so just a quick lesson on that. So, with a deck of cards, and this is a very popular way to calculate probabilities, what is the probability of drawing a king? So we said there's 4 kings out of 52 cards. I'm not going to reduce that, I'm just going to leave it there. We're going to call this probability of K. What is the probability of drawing a diamond? There are 13 cards in each suit, and there's 4 suits. So there's 13 out of 52 cards that are diamonds. And again, if you look at that graphic, you can really see all 13 diamonds. So there's 13 of each suit out of 52. And are these disjoint events? So let me get my deck back out. So that's asking, can there be a king and a diamond on the same card? So there's a king of hearts. There's a king of spades. There's a king, if I can find it, of clubs. And there's a king of diamonds. So those are your 4 kings. One of those kings is also a diamond. So part of these 4 kings is a diamond. And part of these 13 diamonds is a king. So the king of diamonds is your overlap. It's counted here and it's counted here. So no, these are not disjoint events. We're going to call this probability of D for diamond. So what is the probability of drawing a king or a diamond? So K or D. We're going to have to use the general addition rule for this. So the probability of king plus the probability of diamond minus the overlap. King and diamond. So the probability of king, we said, is 4 out of 52, plus the probability of diamond, which is 13 over 52, minus the overlap. There was one card that's both a king and a diamond. So if you leave the fractions unreduced, all those denominators are the same, which makes it easier to do your subtraction. So you should get 16 out of 52. Once you have your final answer, 16 out of 52, you can type it in to get the decimal, 0.3077. On a graphing calculator, there's a button called Math. If you push that button, the first option says frac. What that does is convert your decimal into a lowest term fraction. So it's going to take 16 out of 52 and reduce it for you down to 4 out of 13. So you can use this tool to kind of help you. Again, it's the Math button. And when you push Math, you go to frac, and it puts it in lowest terms for you. So 4 out of 13. So depending on how they want the answer, you might have the decimal, the percentage, or the lowest term fraction. All right, let's see how we're doing on time. See if we have time to talk about complementary events before the video cuts off. It does so automatically, so I never know when it's going to cut off. All right, so another part of section 5.2 is complementary events. The complement of an event is the probability of it not occurring. So I kind of think of this like opposite. So if I know the probability of something winning, I also know the probability of it losing. So the complement of the event rolling a 1 on a fair die is the event not rolling a 1. So everything that the event is not. We use the notation E with a little c as a superscript for the notation. So the opposite of the event, or the complement of the event. So the complement rule says that if the probability of the event plus the complement equals 1. So what you want plus what you don't want always adds to 1, because all probabilities have to add to 1. The way we most commonly write that is the probability of the event not happening is 1 minus the probability of the event. So just subtracting that and moving it to the other side. So I believe that's how it's written in your formula booklet as well. So here's your complement rule. The probability of the event not happening, the complement of the event, is 1 minus the probability of the event. And this is a very important rule. We're going to see it again in section 5.3. We're going to use this. It's a very powerful tool to help us calculate probabilities. So this is just kind of a visual. We have the entire sample space is the entire box. You have your event in the middle, and you have the complement of the event on the outside. So it's a nice graphic to see. We have what we want and everything we don't want. Everything that's not part of the event is what we don't want. So here's just a quick example of that. Let me make sure my video's lined up. So earlier we computed the probability of rolling a sum of 7 on a pair of dice to be 6 out of 36, or 17%. Let's call this P of V, V standing for 7. So what is the probability of not rolling a sum of 7? The complement of this event is going to be 1 minus 6 out of 36, which you can think of as 30 out of 36. So if 6 events are a sum of 7, the other 30 are not. And if we divide that out, 30 divided by 36 is about 83%. So you think of 100% total, 17% sum of 7, 83% not. Here's one more example of the complement rule. Here's that probability model we've seen before with the different colors of M&Ms. So suppose the probability model to the left represents the probability of getting different colors of M&Ms from a regular size bag. In this case, the bag had no reds. You randomly select an M&M from the bag. What is the probability of not getting a yellow M&M? So I don't want yellow. So one thing I can do is add up all the other probabilities. But if this list is really long, that's going to take us a very long time. The quickest way to get the complement of yellow is to do 1 minus yellow. So that's 1 minus 0.15, which very quickly gives us 0.85. You'll get the same answer if you add up all the other ones, but again, this list is sometimes very long and it's inefficient to do it that way. It's more efficient to do 1 minus what you don't want to get what you're looking for. So that's just a quick way of how we use the complement rule. Alright, I'm going to stop there before I get cut off, and we'll pick up with 5.3.